Okay, so just a quick recap. Last time we talked about some parallel algorithm for sorting, right? And one of it is merge sort. And from this basic or naive parallel implementation for merge sort, you can observe a problem that the parallelism, right, the number of processes you can use in each step actually will decrease, right? Especially in the last step, you could only use one process to scan through the whole array. So that means we are not fully utilize the parallel computing power, right? And which will lower our scalability, lower our parallelism. That's why its efficiency is not very ideal, right? So at the end, you can see the parallel algorithm here has a complexity of O of n, right? It's better than the sequential code, but for in the case you use n processes, the ideal complexity should be log n instead, okay, not O of n, okay. So this problem indicates some of the fundamental concept when designing a parallel algorithm, right? That is to explore and to make sure you are able to fully utilize your computing power in your computations. Okay, so so we introduced the bitonic merge sort, right? It's a special case, but if your question satisfy this constraint, that is the number of the numbers you have is power of 2, then you can see over here for if it's a bitonic sequence, right? We can do a pairwise compare and exchange in order to sort those numbers in just out of log n steps. Okay, and the most important thing is we are able to use all the processes we have. Okay, so last time, right, we give you the analysis about the whole algorithm complexity and show you that with this bitonic merge sort technique, then you can further lower your algorithm complexity to the log n squared. Okay, it's still not the optimal complexity for the parallel algorithm, but at least it's better than what we saw before. Okay, so the parallel algorithm itself could be a course to teach that, but for this course, we are more focusing on the programming side, right? The performance tuning side or implementation. But this give you a test about what is like and what you need to consider when try to design or optimize a parallel algorithm. Okay, right? So we followed that by introducing two more parallel sorting algorithms. Again, all those sequential implementation, you already know those sequential implementation, but let's just see how it can be parallelized, right? And the one of it is rank sort, right? If you remember, if you can record, the idea for rank sort is try to compute the ranking of each item, right, in your array. Okay, so for example, over here, right, the most naive way, of course, to determine the rank of an item is to scan through the numbers, right, and compare to the value of your item and see how many of other items has a smaller value than yours. Okay, so after that comparison, then you will determine the rank over here. Like, the value was 1, his rank will be 0, means he will be moved to the first position, so on and so forth, right? So this algorithm basically is separate into two phases, right? First phase is to determine the rank of each item. The second phase is to directly move the item from his current position to his ranked position. Okay, and obviously, no, this is not a very efficient sequential algorithm, because like the naive design over here, you can easily see that the complexity is n squared, right? It's even worse than n log n. Okay, but for parallel code, although it's very simple, right? Because how you can parallelize it is simply say assign a process to determine the rank for a single item, right? So that process simply need to just scan through all the items and determine the rank. And since we have n numbers, we have n processes, so we can just assign one process per item and complete this ranking decision or computation in all of n time, right? It's very simple to implement it, as you can imagine. But you can see the complexity is not bad at all, right? It's actually the same as the merge sort we just talked about. But this one can be implemented much easier, right? And probably involve less communication or synchronization overhead. So the actual runtime for the parallel rank sort might be even better than the merge sort. Okay, so you can see that why we said that for designing a parallel algorithm, sometimes all you care is how easy it is to parallelize it, right? How can I parallelize it without introducing additional communication or synchronization overhead? Okay, so sometimes a naive and non-optimal sequential algorithm actually is a better fit to be parallelized and to become a better parallel algorithm. We will see this again when we talk about the shortest path algorithm at the end, and which will also be your assignment for homework 3. Okay, so sometimes we don't try to parallelize the most or the best sequential code or sequential algorithm. Okay, and furthermore, for rank sort, right, it can even use another trick, that is to use more processes or computing power in order to further reduce the time complexity. And it can do it easily by, as shown over here, instead of assigning just one process to determine the rank of a single item, we throw in n processes to determine the rank of a single item. And how you determine the rank in parallel, you can do it like using a tree structure, right? So for example, right now we just try to determine the rank, okay, for maybe just the first element, right? And we have n processes, so we can use a tree, right, to compute the sum, right? How many items are smaller than this given number, right? So we have 4 items, and we throw in 4 processes to do this computation. So each process just in the first step compare it with the value of 4, determine whether it's smaller or large equal to the number, right? And then just do the sum, right? We can recursively aggregate the result. Okay, and of course you can see by doing this, the complexity, right, to determine the rank of an item can now reduce to just all of log n, right? And remember, we throw in n squared processes, so that means the rank for each item can still be determined in parallel. Okay, so the log n time for a single item will be also be the time complexity for the whole algorithm, right? So we use more processes to achieve even better time complexity. Okay, and we can do this quite easily, right? However, of course, the penalty is your efficiency actually will reduced, right? Because the total time complexity should be n squared multiplied by all log n. So this actually worse than the bitomic merge sort we introduced. Okay, but this technique is also quite common when we try to design a parallel algorithm. The technique I mentioned referring to the trick that you try to throw in even more processes in order to get a better overall time complexity. Okay, and with the sacrifice of your payroll efficiency. Okay, all right. Okay, and so the last sorting algorithm we want to talk about is the counting sort. Okay, and the idea of a counting sort is to generate the histogram of your numbers. Okay, so histogram, as you probably should know, is given a set of bins, right? And you try to put those number into those bins. Okay, and then you can calculate how many items are in each of the bin. So you can use that to determine, right, how many numbers are smaller than you or larger than you, right, from the distribution of the histogram. And so what you need to compute from the histogram is the prefix sum, right, for each item. And then use the prefix sum as the index, right, for your new position. So you can get the sorted results. Okay. All right. So this technique again it's possible, right, to reduce the complexity to just O of log n with n processes. Okay. And if you look at those steps, we can quickly analyze the complexity over here. As you can see, in order to build the histogram, we simply need to check the value of each item and use the item as the position of your histogram array, right? So with n processes, you can complete this step in the time of O to 1, right? And then you need to do a prefix sum. And again, you can use a tree structure like we just showed before. Although that's computed the sum, but prefix sum is very similar, as you can imagine, right? Just recursively reduce to add the number of items that is before you. Okay, so again, you can use log n time to compute the prefix sum, and then again, each process is responsible for moving one item to the sorted array. So that's again O of 1 time, a constant time. All right. So overall, this complexity is just O to log n. Okay. Okay. So although it looks to be the optimal solution, right? But as we know, counting sort can only apply for a special case or with some constraint. The constraint is that the bins, the number of bins, right, should be it should be a constant, or it should be a small number, right? Otherwise, when you do the prefix sum, the complexity you cannot treat it as n, right? You have to add the value for all the bins, right? If the number of bins are more than the number of items, then the time complexity will increase. Okay, so as a result, we know that for counting sort, right? Even for sequential code, it's it could be faster than n log n. So over here, actually, compared to its own sequential algorithm, is still not the optimal complexity. Okay, but of course, the parallel algorithm still reduce the complexity by a certain degree. Okay, all right. So summarize, right? Because sorting is very common, and there are many sorting algorithms, right? And can be taken as example to understand how a parallel algorithm are different from a sequential algorithm. Okay, and as you can see, right, as we mentioned, it's still very, very difficult actually to achieve the optimum cost, right? We can easily reduce the complexity with parallelism, but it's not that easy to achieve the optimal complexity. Okay, and we show you some techniques, right? Like Platonic sort, how you can probably further optimize a parallel algorithm, or the rank sort, to show you how you can throw in more processes to achieve better complexity by sacrificing your payroll efficiency. And finally, some of the special case, like counting sort, it is possible to reach O log n, but it is with some constraint. Okay, all right. So that's it for our no no our first example. Okay, and all those you can see they are right. They are recursive algorithms. That's why we classify them as example of the divide and conquer strategy. Okay, and you can see that most divide and conquer strategy can be easily parallelized, but at the same time, usually it's very difficult to reach the optimal time complexity, because your recursion steps usually involve some dependency, and which will reduce the parallelism. Okay, all right. And the second example we're going to introduce today is unbody. Okay, and as we mentioned, this is a very well-known scientific application for simulating the movement of the planet. Okay, and as we learn from our high school, right? The reason those planets will move is because of the gravity, right? It will generate the force. And I think we all know about this famous equation, right? And so as long as your object has some mass, then depends on the distance, it will generate some force between those two objects. And the force will generate your acceleration, right? And then turn to increase your velocity and move. Okay. Really quite simple, because it just try to iteratively determine or compute the location of those planets according to the equation above. And our simulation will basically try to update the position of those objects for every time intervals. So if we play the result over a long period of time, it will become a video, right? It will show the movement of the planets in our sky. Okay. So again, this is what you probably know from high school, right? So basically, we have X indicate the position, we have V indicate the velocity, and A indicate the acceleration, and we have T to indicate their values at a given time interval, right? And just as I explained, right, we all know that's how we could eventually determine the velocity and the position for each item for any given time, okay? According to their location and the mass from the previous time interval. Okay? Right? So those just the equation we're going to compute. And of course, the example we had before is just one dimension, the x dimension. But in reality, right, in the real world, we know it's a 3-dimension. We have x, y, z location. But according to the rule of those force, they can be computed independently on each dimension. So it actually doesn't really matter too much, right? We just follow the same calculation for each of the dimension. Okay. All right. So So the n-body simulation, if you think of it, it's not that complicated at all, right? Basically, we have several for loops, okay, and on the outside is the for loop over time, right? It depends on how long we want to simulate it, okay, how many time steps we want to simulate the result, and then we have a for loop, right? Scan through each of the items. And each of the items need to compute the force, right? Generated from other objects. Okay. And so you can see that this compute force, of course, it alone takes all of n, and you have no n bodies to simulate it. So you have n squared. And of course, you consider time step, then that's the complexity will grow even further. Okay. So overall, if we don't consider time step here, the algorithm itself, as we know, if it's sequential code, then the complexity is n squared, right? It might not seem too much, but in the planet in astronomy study, the number of objects or planets can goes to millions of objects. So this complexity is still very, very time consuming and sometimes prevent us to generate the results. Okay. Okay. So how can we reduce the complexity? Okay. The way to reduce the complexity we introduce here actually is not for or from parallel computation. This is just a general way to reduce the computation. But as we will see later on, because we have n bodies, right? So after apply this approximation algorithm, we can see that the computation can be further optimized or parallelized. Okay, if we have n processes or we have some parallel computing power. Okay. So the approximation algorithm we introduce here is based on the concept that try to approximate the force among those objects by clustering the objects that is in the near location and into just one virtual objects. Okay, and the idea is because we know the force, the strength of the force is depending on the distance, right? So if there are many items or many objects, right, they are in a very close neighborhood, and all of them are far from the objects you try to compute the force, then all those near neighbored objects can be approximate as just a single objects with the accumulated mass from all of them, right? So you need to, of course, calculate the mass century of those objects. And then you can just simply treat those items or objects as a single object. And then, so it will reduce, right, the number of objects in your problem. Okay. All right. So I think everybody again knows how to determine the mass century of a set of objects, right? This is again from the high school science class. Okay. So, okay, with that concept in mind, then for those simulator, they basically try to recursively determine how we could approximate those objects according to the relative distance to the one we're going to compute it. Okay, because you can see that the approximation is depending on which item, right? Which object you try to compute the force, right? So for each object, its approximation result, or you could say clustering result, will be different. Okay, so so the question becomes how we can determine this approximation given given object we want to consider. Okay, all right. So In this example, okay, say the object we want to compute the force is this one right over here, okay, and the black dots over here are the real objects, okay, and we try to determine, right, what are the objects that could be clustered together, right, and so you can reduce our time complexity, okay. And of course, this determination need to follow some approximation rule, right? So the idea here is that if we can proxy them as a cluster, if the distance from all the objects in this cluster, its distance is much smaller than the distance from this central mass to our object. Okay, this is because we consider this condition because this is exactly the basic concept of our approximation, right? So if we say the distance from the mass century to the object is r, okay, and say the diameter of this circle, right, that include all the objects, okay, is L, right? Then L should be much smaller than R. Okay, if it's smaller enough, then we can approximate them together. Okay, and the ratio between R and the L, of course, become a threshold, right? A parameter in our approximation algorithm. Because if we want the ratio to be, say, larger, then that means we have a stricter condition for approximation. Okay, all right. So so that's the idea. So basically, we need to determine, the relation between R and L. Okay, and so how we can determine it efficiently? The famous algorithm called the Barnes-Hart show here. We show over here. What he tries to do is he will build a data structure, okay, in order to represent the location, the relationship of the location between those objects. And what it does is that you can see this is we just consider a two-dimension problem as example, okay. And what we need to consider is a space, right, a two-dimension space, and we can recursively divide the space, right, along the x dimension and y dimension, so we can generate those smaller space partition, right, from our problem. So for example, you can see every node in this tree structure represent a space, and we start with the global space that the root over here represent the whole space. And by recursively divided along the x and y, we generate 4 smaller space, right? And then we can recursively doing this, right, by partition the space with objects to even further smaller space. Because at the end, we only care about the space with object. So you can see, for example, here, the leftmost node, we don't further divide it because you can see in this space, we have only one object alone. So there's no meaning to, it doesn't useful to further divide it because the single dot can already represent the whole space. Okay. But however, for the other 3 subspace, you can see we still have more items in there, so we can further partition it, right? And again, we only care about the partition with objects. So that's why you can see this tree may not be fully grown, right? You will you will have less or fewer branch according to the position of those objects. Okay. But anyway, at the end, you can just keep repeating this. So this is a tree we can build from this input problem. And you can see every leaf node in this tree, okay, represent an object in our problem space, right? And the color or the level of those nodes represent the size of this partitioned space. Okay. And why we want to so why are we doing this? Because right, if you look at it more carefully, then you can see this is actually what we try to do is try to recursively partition the objects, right? So that the objects in the near neighborhood, in the near distance, will be fall into under the same subtree, right? For example, all those three nodes are or objects, they are very close and they are within the same pink area. So they falls under over here. Okay. So in this tree, what we're going to store on each intermediate nodes are the information that can approximate the whole group of objects in that space. So that is, for example, the central mass of that cluster. Okay, so you can imagine every node over here is a approximation result, or it try to represent a cluster of objects. Okay, all right. So that's the data structure we want to build. Okay, all right. So after we build that, how we can utilize it, right, to determine how we actually going to approximate the force for respect to with respect to a given object. Okay, for example, like the dots over here. Okay, and the way we compute it is, as I've just mentioned, right, whether it can be approximated depending on the theta parameter or threshold. Okay, its calculation is d divided by r. So r is, as I mentioned, should be the distance from the object to your central mass, and d is what I said is L. So sorry to confuse you, but I should say d before. Okay, so d is basically the diameter, right, of that cluster. Okay, so if d divided by r, right, is smaller, is small enough, because we want r to be as large as possible, right? If it's small enough, then we approximate. That means we can treat the cluster as a single object, and we don't need to further examine the force generated from the objects in that cluster one by one. So we can reduce the time complexity. Okay, right? So how we can combine them together is, for example, we want to determine, right, how we can cluster all those dots with respect to this A point. Okay, so we will do that by start traversing the tree structure from the root. Okay, and the root, if it stop here, that means everyone treated as a single cluster. Of course, it's impossible because even A itself is within this cluster. So of course, usually we will it will not satisfy the condition of theta, right? The value you computed, D will be even probably larger than R. So it doesn't satisfy our condition. So in that case, that means we need to we need to further partition the space, right? So that means we need to go down one level to examine those 4 sub-partitions. Okay, and we will again follow the same same evaluation to determine whether our calculation can stop at some certain sub-partition or stop at this cluster. Okay, and we need to examine the cluster in each of the space individually, right? So the rightmost one, right? So let me see if we have, yes, we have the example over here. So we will recursively traverse the tree, right? And so first we examine D, the intermediate node over here. So when we examine it, means that we assuming the cluster D over here can be approximated as a single object. Okay. Sorry again, we should be more consistent, but now we we want to compute the force for this relative point x. Okay. So you can see that, right, those items are pretty far away from x. Okay. And the diameter of those cluster, usually we just approximate it by the length of this square. Okay. So this length of the square is the d we mentioned over here. So for d, we can divide his length, right, diameter d, to ar, means this distance. Okay. Okay. Over here, now rd is 20. Okay. So we can compute this to calculate this theta, right, for each of the subspace. Okay. And in this case, you can see D, the item in D is very close to each other, and all of them are far away from X. So that means, let's just say it's satisfy our theta constraint. So that means our calculation can stop over here. This whole subtree, we don't need to further iterate that. Okay, we can just treat it as a single object D over here. Okay. And same thing, right? For C and B and A, we will stop here as well because A is a single item. We cannot, it's already the leaf node. So of course, this object in A will treat it as a single object in our computation. Okay. But for B and C, you can see, although C, they are pretty close to each other, but they are also pretty close to X. So for example, let's just say, no, the ratio doesn't satisfy theta. So that means we need to further break C to smaller subspace. And as you can imagine, right, after you do that, then this subtree, right, P plum over here, the diameter will further reduced. So it has a better chance to satisfy our theta constraint. Okay. And the C plum over here, it become a single object. So of course, you don't need to further extend it, and you will treat it as a single cluster, right, in our computation. All right. And finally, B over here, X is the object itself, and A plum is also a single object. It's already the leaf node. So in this example, the number of objects we need to compute the force will be D, C plum, B plum, A plum, and A. So it's only 1, 2, 3, 4, 5. Okay, so originally, as we know, this probably have 10 objects, but for our approximation, we only need to compute the force from 5 approximated clusters or objects. Okay, so that's why we can reduce the time complexity. Okay, all right. And as you can see, this tree structure, we only build it once for all the objects. But for each object, you have to traverse the tree itself, right, in order to determine the correct approximated partitions respect to that object. Okay, so that means every object need to traverse the tree on itself. So if we have n nodes or n objects and we have n processes, then what happens is each process will try to traverse the tree like we just described. Okay, and all the objects will try to traverse the same tree at the same time, but they might resolve to different partitioning results. Okay, because their location are different. Okay. All right. So so you can imagine there are a lot of parallelism opportunity, right? Including when we build a tree, we can use n processes to build the tree to accelerate this computations, right? Because you can imagine, like for example, after we break the space to A, B, C, D, then we can probably assign 4 processes to further, right, divide it and to build a subtree. Okay, and the parallelism degree actually can be increased as we go down further. Okay, But of course, it's not perfectly, it cannot be perfectly parallelized because, for example, at the beginning, we probably can only use one process, right? And then we gradually increase the number of, degree, parallelism degree, okay? So it's not ideal. You have some dependency, within the computation. So, of course, how to design and implement an efficient parallel algorithm to build this tree and to traverse this tree become, well, the problem for parallel algorithm. Okay. All right. But anyway, you can see that it's definitely can be accelerated by the parallel computation. Okay. And theta, as we mentioned, is a parameter, right? Because if the theta is smaller, then that means it's harder, right, to approximate the objects into a cluster, right? So if theta equal to 0, you will never meet that condition until you traverse to the leaf. So actually, you cannot reduce any objects. So your time complexity will not be reduced. And the overall computing time probably even increase because you have to build this tree, okay, and traverse this tree. Okay. On the other hand, if theta equal to 1, it considered to be a very, right? Because essentially that means those items different cluster or at least different partition, then they can be approximated as a single object to the object you want to compute it. Okay, because theta equal to r, that basically means, right, your target object is basically within the same partition. Okay, so 1 is already a very, very loose bound. Okay. And of course, you can imagine with larger theta, you can reduce your computation time, but your result will be less accurate. So you can see this is true for many, many approximation algorithm for scientific computing or or some problem solving application. Okay, it's a trade-off between accuracy and computations. Okay, or computing power. Okay. And also for this technique, it has a drawback that the ideal complexity can only be reached if the tree is balanced, right? If the tree is not balanced, right, you probably have less chance to approximate them together, or you have to traverse the tree deeper. And so usually that will increase the time complexity or the overall, the actual computing time. Okay. So how to build, how to make the tree balanced is a problem. Okay. So, and of course, this tree need to rebuild for every time interval because every time interval, the objects will move, their location will be different. So you still need to rebuild this tree for every time interval. So that's why N-body is considered to be an application with very high computing demand. Okay. All right. So how can we at least address the problem of unbalanced tree? Okay. So to address that problem, there's another algorithm is proposed called this orthogonal recursive bisection method. So the idea is to make sure the tree we grow is balanced, and we can do that easily, right? The concept is to make sure that every time we partition the space, there are equal number of objects in each subspace. So that means when we do the partition, we have to consider the location of the objects, right? And we will recursively partition the space along each of the dimension. So over here, it will build a binary tree. Okay, that's why it's called the bisection method. Okay, and for example, we start with the x dimension. So we try to find a point along the x dimension that will evenly divide the objects in the space. And so, for example, this is the position we find. So that's how we determine where we partition the space. And as you can see, right, the number of dots on both sides are roughly the same. Okay? So again, same as before, we build this tree, and you can see because every time we ensure the number of items in each space are equal, so we can always generate this binary tree. But you can see the partition, right? After we divide by x, for each blue space, we divide it along y dimension, and they can be cut at a different position as long as the number of objects are evenly distributed. Okay? So not too hard to imagine, right? So at the end, this is the tree we're going to build from the same problem we've seen before. And you can see the tree is very, very balanced as it can be, right? So this addressed the balancing problem. You can ensure the workload could be more balanced. But however, this method actually usually will reduce less accurate results. You have better computing efficiency, but less accurate result. Because you can easily see as example, those two dots, they are very close to each other, right? However, when they partition the dots, it only consider the count of the dots, not the position of the dots itself. So even though those two objects are so close together, unfortunately, they can be partitioned into different branch. So that means they have no way to be approximated as a single object. So that's why you can see it's a trade-off. In order to make sure that the tree is balanced, sometimes we ignore the location. As a result, this approximation has worse accuracy than the previous one. So there's always some trade-off. And the two methods we introduce here, they are quite famous, and they are sometimes the basic form for solving this problem. And the real application, of course, they will try to improve over those techniques. Okay. But anyway, because this is also a recursive method, so you can consider as a divide and conquer algorithm. And you can see there are many places can be parallelized, right, to reduce the overall computing time for the n-body simulation. Okay. All right. So that's it for the divide and conquer computation. And the next lecture, we will move on to the pipeline computations.